So what are we doing today? Today we're doing Cirque. So I decided, we gotta practice. We really gotta practice. And before I moved the whole thing to StrangeWorks, we're basically gonna practice me more. So, and I recently saw someone watch the YouTube Shor's error correction video. This one. And one of the second part. And so I wonder actually where I left, because I did indeed call it part one, but I can't really remember where I left. So sorry, this state. And so this zero makes these two gates, they don't take place, but then this last one basically self-corrects and puts it back to one. If we were going to do the opposite, say, this is a 0, right? And that flips it into a 1. Well, then basically those two things trigger, and then again, that last Toffoli gate corrects it back again. So that's the mechanism. Now it works for all the other states because of the linearity of quantum computing. So I think I'll have to finish it in a second. You would still have. So what you still have now is the. So how does this? But I think I didn't explain the phase correction, did I? Computing, literally. Okay, so because what I wanted to do is I wanted to basically get a bit more practical and kind of merge two ideas, and the one is keep analyzing, keep taking a look at Shor's error correction code, but kind of implement it using Cirque and kind of do a bit of an exercise where I would maybe implement some kind of registers that where's the code? So basically implement that whole circuit as a one logical qubit and then try to play with it and see if we can create like a small circuit and translate it into a circuit that basically has Shor's error correction in it. So this means, what would it look like to apply an X gate to such a logical qubit, right? Would it mean apply an X gate to all the wires? I guess so. So that's my point. I want to try to do something like this and then see whether we can play with that and even add some kind of noise model to it and kind of compare with a perfect simulator and a noisy simulator. Yeah. So let's see. Shor's correction code. So, and I'll move those things. I'll move all those things to StrangeWorks as soon as I'm able to do that. But basically, and at the same time trying to learn some Cirque, right? Because I used it only once I went through the tutorial, but I kind of really forgot. And I just want to get a feeling of how is it working with Cirque in comparison to Qiski as well. And kind of, I just need to practice, I guess. I just need to practice Qiski, practice Cirque, practice maybe Forest as well. We'll see. So we first need to basically, let's start by quickly prototyping these. I want to make a function that basically gives me that first part of here before the actual operations, right? Before the actual correction. This is the first kind of encoding part. And so for this, I need like 1, 2, 3. Okay, so 9 qubits. So how would you do this with Cirque? So you got circuits and you got basically conceptual overview, constructing circuits. So this is a circuit, classical collection of moments, collection of operations. Circuits and another kind of object defined by instance of subclasses of the QID base class. Different subclasses of QID can be used for different purposes. Okay, 3x3 create qubits by doing these. So with 3x3, we would have 9 qubits. That could be a thing to do. Do they always have to be in a grid? That seems to feel a bit awkward first, but I think it kind of also makes sense because that's how the chips are really organized. Constructing circuits, circuit append. I remember reading somewhere here that it's not necessary for them to be in a grid. Build one begins by building a person. And circuits are represented by a circuit object. Special moments. Okay, so it's kind of the same. The problem with defined natural fits in a grid will use Circ's built-in grid qubit as our qubits. We'll demonstrate some of the how it works. Okay, but it's not necessarily the only thing that's available. I don't know. Circuits, but let's go with this. I mean, it actually does fit as well, because for me, like you would say, I would say maybe let's just Shor collection. We'll just open the Wikipedia. Sure. So it's kind of, you know, each of those three. It's basically a you could consider them a register, right? Or you could consider each of these three as, so these three, and these three, because they're basically copies of the first three, of the first one. So those are, okay, so this is basically a copy of the amplitude. You're entangling these. Yeah, and those things do a phase correction, I think, right? Was it, I think, was it this way? Yeah. Good, so we'll do that. So actually, so that's, okay, so we're going to create a, yeah. So what we'll, okay, so let's create that for X. So I'm qubits. Basically, it's an array of circ qubit xy for X in range 3, for Y in range 3. Qubits, then I get the qubits in here. That's good. So I've got the qubits now to represent that little thing in here. We'll pack all this into an operation at some point, okay, into a function that will kind of yield that portion of the circuit. Because eventually what we want to do is we want to kind of have a function where you input a circuit that has like n wires, and then for each wire, we will turn each wire into this beast. The next level, so we've got the gates. Okay, we don't really care about the gates, right? No, we do care about the gates because we want to build that first. So, cross qubit. So these are the gates. This is an operation. Okay. So gates are really like, okay, so gates are really like classes, and then you can actually, not classes, they are functions, and then, okay, yeah, interesting. So circ CZ on the qubits, circ X. Okay, so circ X or CZ. Okay, so we're probably going to do now something like these, right? So we're going to do something like okay, but what's the circuit? I mean, you don't really have any. You don't have an actual circuit object, I see. Do you? Oh, you created here with the different moments. Okay. Constructing circuits, or you're appending operations to the circuit. Okay, but that's cool. It allows you to define things independently from a circuit first. Whereas in Qiskit, you gotta kind of define a circuit always, right? Um, so you'd say I've got this bunch of qubits, and then you need control nodes between 0 and 3, and between 0 and 6, right? So you would say and I need to store those operations, right? Now, that's an awkward way of building, so I need to create a moment with those things. Do I need to create the moments? It's tedious. And instead of provide the variety of minus to create a circuit. So you can append the stuff in there. Okay, so you can append the operations. Okay. And you can do that like the circ operations. Import. Okay. Okay, cool. So you can actually do from, or isn't that already? Okay, so just to make the notation shorter. So from circ ops import CZ H CX X. Can I do something like this? I don't know if I just did it stupid or not, but can I do like can I do X QB 0 and that being like an op and now sorry qubits 0 and now print op and what happens? Okay, so it does work. Now, how do I remove an operation? Okay, I don't have to remove it, just that operation. I could just ignore that. Okay, that's nice. That's neat. Okay, so I can just say basically my circuit is equal to, so we create a circuit and then we append the operations that we want. So we say circuit and here we go. So now we do basically the first things in here. Okay, so we do in order, right? So we do a control X qubits 0 and qubits. Can I just can I do it like these? I think it's gonna make my life easier. Qubits 0 and qubit 3, and then we do a CX between qubit 0 and qubits 6, correct? And then Hadamard gates. So then we do basically Hadamard gate on qubits 0, Hadamard gate on qubits. It feels rother than Qiskit. It feels a bit better somehow, or even a tick more flexible so far. And then we're gonna do control nodes between 0, 1, 0, 2, then 3, 4, 3, 5. Okay, so we're gonna do like so 1, 2, 3, 4, 5, and it's going to be 7, 8. And we are, I think, good to go. This is the encoding part, and then decoding. Encoding circ, I'll call it encoding circ. And if I now do this and I print encoding circ, what do I get? Beautiful. Those things in here. Okay, but that's one moment, and then there's this Hadamard in here, is it? I guess so. That's this. And then the decoding part, it's kind of the same operations, but backwards. So we will basically now kind of copy this and have it here and call it decoding part, decoding circ. And we're kind of going to have these things go first. Okay, and repeat them. Then we've got like, so then we've got actually here a, how do I so circ operations now. Let's see. Have we got any CCZ? Is there a CCX? Power inverse, blah blah blah. Where can I see all the other gates? Can I see all the other gates somewhere? Other common gates? Oh, that's where I was. Circ. CCX. There is. Okay, it's there. So I can actually use it. CCX. And this is basically qubits 2, qubits 1, qubits 0. Right? So we're building that part in here. Good. And so this is going to be here. This is going to be here. This is going to be here. So I kind of, one thing that I like is that it's almost like building a circuit is less programmatic, and it's a bit more because it's a bit more like just append these gates in this order, which you can have both worlds, which is kind of good, which is kind of nice because you it's a bit more like building an actual graphical circuit. I don't know if you can do that with Qiskit. Probably you can, but so this is going to be 5, 4, and 3, and that's going to be that's going to be 8, 7, and 6. Now we've got the Hadamard gates again. So we're going to do that. Then we've got the Hadamard gates. Now we got a, okay, now we've got basically the 0 to 3 control X, the 0 to 6 control X, and we've got a CCX green. Qubits. So we print basically qubits 6, 3, and 0. That should be the decoding. Okay, where am I missing? I'm missing commas in here, commas in here, commas in here. It's not defined, CCX. Why is it not defined, CCX? Circ CCX. Circ Toffoli. API reference. Gates operations CCX. Should be, oh yeah, well, you kind of, no, I should probably import it. And if I now print the decoding circuit, coding circ, I get that this beauty here. Okay, cool. So we're good to go with the basic functions to encode these things. Now, question is how we're going to make, for example, how we're going to translate an X gate, right? So that's going to be my first test. It's like we need the encoding part, then we need to apply our operation, but across all the qubits, and then the decoding part, and then we need to measure. And what we need to measure is the qubit 00. So exactly, right? So how do we do this? Can we, now that we've got these circuits, can we just append circuits? Can we just do something like test equals circuit, and then can I just do test append, for example, encoding circ, and then test for encoding circ, and then decoding circ. Can I do something like this? Okay, print test. Wow, you can. That's good. That makes it easy. Pretty simple. That's cool. So, unitary, what is this? Okay, so gates. So we're done with gates. Okay, there's noise simulation, etc. Now, let's see, right? So so what would be an X gate, right? So for example, if I want to apply an X gate to a circuit, I just do the X like that, right? But if I want to, I've been doing here, but if I want to say no, my Shor X, right, which would be the X applied to that logical qubit, it's actually an X gate, or it's actually, yeah, these, right? So an X gate applied to it's an X gate applied to all the qubits, which we can basically do X qubits X for X in range 8. I print Shor X. No, sorry. If I do, okay, so now if I do, how can I? So if I hit the circuit, how can I actually reset the circuit? Because I only just have append. And deny circ remove gate, remove operations. Remove batch, remove fermentation, remove key. Remove several operations from it. So if I do go to the beginning, it's a batch remove, batch insert, batch remove. Self. several operations circuit. Hmm. But how do I pass this as an iterable tuple circle operation? Batch remove. Doesn't exist. So I actually need to do something like pet batch remove sample decoding circ. Can I do this? Too many values to unpack. Mm-hmm. And start with IDZ gate. Circuit with the docs. Remove operations from circuit. Remove. Batch remove. A sequence of tuples indicating operations to delete from the moments that are present. All these operations must actually be present or and it will fail without any chance to the circuit. Yeah, or I might just as well start from scratch. Why would I need to remove that? Okay, yeah, why do I need to remove that? So I can just basically take that again and replace. So and now we're gonna do test append, and we're doing the encoding circ. We're appending Shor X, and we are printing test. Yeah, this, exactly. So there's an X everywhere. Okay, cool. And so now I could basically test append decoding circ and print test. And now I got the whole thing, the whole monster in here. Okay, good. How do we simulate this thing now? How do we simulate this thing? So simulation. Good. So built-in Python simulation testing small circuits. Just in pure state simulation. Here's a sample circuit. So you've got the circuit. So what is this yield thing in Python, by the way? Python yield. It's returning Python, geeks for geeks. The yield statement suspends function's execution and sends a value back to the caller that retains a not state to enable function to resume where it is left off. When resumed, the function continues executing immediately after the last yield run. This allows its code to produce a series of values over time rather than computing them at once and sending them back like a list. So yield 1, yield 2, yield 3. So for value in some print value. So it's like multiple returns. That's fancy. Okay, that's cool. Good. Where were we? We were here. So you've got the basic circuit. And then so circuit import simulator. You create a simulator and you just run the circuit. Okay. It's fairly simple. Okay, really? So if I do from circ import simulator, so from circ simulator simulator, and then we're here and we do basically what simulator and result simulator.run. Okay, so and then we do basically result equals sim.run and we run the whole thing test. Boom. Okay, so what's going on here? There's no measurements to sample from. Okay, so we gotta have measurements. And so the measurement, okay, so how does it look like with measurement? Circ measure Q0, you can give it a key. You can give it a key. So circ measure. So I would still have to do first then test. That's different because that's not you're not appending an operation. That's interesting. So it's just measure. Okay, but okay, so test measure, and then you're saying qubits. So we want to measure qubit 0. Okay, measure qubit 0. So no, actually measure. So what is? Oh no, circ measure. Oh, it is indeed an operation. Okay. So actually, you do append, then you do circ measure. Of course, it's not the circ measure, and now you say qubits. Also, you say from or from circ import measure as m. Can you do it like this? Now I can basically say append m qubits 0. So we measure qubit 0. And we don't need to give it a key, I think, because it's the only thing we want to measure. But we can. I mean, what's the advantage of that? Is that you can then refer to it while building some statistics, I think. Key 0. Okay. Does this work? Does this work? Print test. Okay, we got the measurement here. Good. Let's run this thing then and see what happens. Okay, so we run it. Similar to mimic what running a program with a quantum computer is actually like. So how do we get? Oh, okay. So we can print the result. The result are just what? The result is just what is the result? The you can set this give access to the wave function. It's the simulate method, simulate sweep, simulate moment steps should be used if you want to debug the circuit and get access to the full wave function. Simulate is simulate. Okay, run does the whole run. It just runs it once. So simulate. Simulate can take the type of if higher precision is needed. Outside, inside. What is this? The qubit order argument of the simulator's run method determines the ordering of some results, such as the amplitudes in the final wave function. The qubit order argument is optional when it's omitted, sending by their name. Simple simulator can provide a list of qubits. Okay. So you can reorder the qubits. Well, the kth amplitude in the wave function will respond to the kth case. That will be okay. Can check if has the ordering of the circuit. Stepping through the circuit. Okay, so that's stepping through the circuit. Oh, look at this. You can step like that. That's pretty nice. you can steps through the circuit. So can you do that in Qiskit as well? Circuit. Change the steps inside. I don't think you can do that. Because that would allow me to do the same stuff that I've done for Quirk with this amplitude, with this interference inspection to build something with Circ. That's kind of cool. Okay, and then we've got some noise simulations. But what about, so why is it 0? That's the point here. So let's take a look at this. So simulate final state, NP around final state 3. What does this mean? What is NP around? NP around. What is NP around? Evenly round to the given number of decimals. Okay. So the current is optional then. How do I, why does these kind of seems like it's getting that's looks really messy everywhere. Where are all my x's in here? Test. Have I done this well? Shor x. Shor x. Where are my x's? Where are my, oh, here. Decoding circ. What have I done? Why this looks like this just a lot of stuff in here. That's not. So give me a second. Okay, so let's so if I do this, then that's it. Okay. Now test is that thing. So if now I go and I run a simulation, okay, and I need to add the measurement. So I'm gonna add the measurement here. Okay, so now I got the measurement, and now I do the simulation. I get that. If I copy these, where am I? Here. If I copy these here, I'll just call it test X, not to start getting confused in here. And I get rid of these. So if I do these, I get this beautiful circuit, encoding circ. Why? Okay, so first of all, edit, delete cells. So I do these. I print test X. Okay. If I now add the Shor X in here, okay, that looks better. Now I do a test X simulation. C0. I thought I would see a 1. I thought I would see 1 because I'm adding x everywhere. Mm, maybe I'm wrong. Maybe I maybe this just should be the Shor x should just be x on qubit 0, x on qubits 3, and x on qubit 6. I'm expecting a 0, a 1, sorry. Valid syntax? Invalid syntax? Why? Why is it invalid syntax? Can I just do this? Can I not just define an array like this? Should be able to. Qubits, qubits, qubits. Come on. X qubits. Oh, here. I'm missing the parentheses here. Okay. So, and now I go here, and we just have those x's in here, and then that's also not a problem here. Let me try. Maybe I'm not reading the results properly. What if we don't add the decoding part? We now measure. Okay, we're not reading the results properly. What's going on here? Test X result. That must definitely be a. Oh no, it doesn't have to be, because I hotmarred it here, right? What? So, but if I, okay, so at least I need to add those 2 other beats in here. So if this is 0, right? There's going to be 0 plus 1. Times these guys in here. Now XXX. I'm not. Maybe I'm just understanding this wrong. So the problem is I'm trying to understand how would you apply an X gate to such a logical qubit, right? So if you'd how would you apply an X gate? This needs to be part of. How would you do that? It must be like you apply an X gate everywhere, because how could we debug? So how could we debug this? Because then you got that circuit, and then so if this is 0, things go in here. So you've got everything 0, but if everything then here, you apply it like an X gate everywhere. It really certainly feels like that's what should happen. Can I see what the Wikipedia page for the bit flip code? Exactly. So this is So this is, so you need that. So this is for the phase. The Hotmarts do the phase fixing, right? I mean, those parts do the phase fixing. Exactly. Yeah, the bit flip, I understand. But how can I test it here? That's the thing. How can I test that this works in here if it's not applying X's everywhere? How should I do? Am I reading the results well? That's the first thing. So how can I know this? What about the simulation in here? So you can take a look and step through the step through the different things, through the different steps. So what are these 1 and 0 in here, right? Can I not tell it the shots that I want, or is it just probabilities? Or this is just counts? Result histogram. So here, result. So you can say repetitions 100. Okay. Repetitions 100. Okay. Okay, now we're talking. Okay, now we're talking. Repetitions 1000. Okay, and now I can actually do. Okay, cool. So let's do the following. So let's go back to these being what we want. This being the circuit that we want. No, that's not. We want decoding circ here as well. And now we do that, and we apply X gates everywhere. And now we do these, and now we do these. It's all fucking zeros. Why? 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 Okay, so it's definitely not working. So that's not how you should apply it, is it? Can I just print result histogram key A? So result histogram key, and I give it the Q0. Okay, so that kind of gives us the counter directly, 1,000 zeros. Great. Okay. Anyway, I'll leave it here. So basically, I'll leave it here for now. So I'm gonna definitely do at least 2 more parts on these. So I want to figure out how would you apply a logical X gate to this logical qubit. That would be my first. Damn it. Really, if it's not like qubits, should be really for all the stuff. Like it should be for all the qubits that we're applying. How would you otherwise do it? I mean, would you apply a next gate to what? To just these? That could be another option. Because maybe the first part is for the maybe the first ones are just for the entangling. Yeah, maybe that's the thing. And this is for the bit flip. So I'm just basically got it backwards. So you would apply an X gate here, and then so these would kind of become. If I would apply an X gate, both X gates in here, so The challenge is each bit flip, sign flip, face or both. It's possible to correct for both types of code in the short codes. The first, fourth, and seventh qubit are for the sign flip code. First, fourth, and seventh for the sign flip code. So that's for the phase. Exactly. For the B flip code. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, but the actual groups, right? Like so. So if I would apply next gate, maybe I need to just apply to the first three. Maybe I just need to apply to the first three because the other ones are just then being entangled. Maybe that's the point. Just to the first three. Let's try it out. So what if I just say that the Shor X is just for the range of 3. So I come here and I do this and I do this, and so there are just these 3 ones in here. And now I run this. No, it's the same. How would you do that? Okay, that's going to be for the next. That's going to be for the next part in the series, I guess. Cool. But basically, that's what I'm trying to do. So I'm trying to build a logical qubit out of these. I know it's probably pointless, but it's just I think it's a nice exercise to get used to circ as well in the way to build circuits. Kind of, yeah, kind of. I think it was fun. I feel quite comfortable with circ. I have to admit, so far. Perfect.